Critical paths. The critical path in parallel and distributed computing is the longest sequence of dependent tasks in a program's execution graph. It determines the minimum possible execution time of the program. Tasks on the critical path must execute sequentially and have zero slack, meaning they cannot be delayed. Any delay in a critical task directly increases the total execution time. Therefore, the critical path represents the main performance bottleneck of the system. When a client sends a request, the first step, T1, is request reception, taking 2 milliseconds to reach the server. Next, the server performs authentication, T2, which takes 4 milliseconds. After that, 2 tasks run in parallel. T3 fetches data from database 1 on node A in 6 milliseconds, and T4 fetches data from database 2 on node B in 3 milliseconds. Both must finish before the next step. Then, T5 aggregates the results on the server in 2 milliseconds. Finally, T6 sends the response back to the client in 1 millisecond. Although T3 and T4 run in parallel, the total execution time depends on the critical path, T1, T2, T3, T5, and T6. Any delay in these tasks delays the whole response, showing why the critical path is essential in distributed systems. In this system, T1, request reception, happens first and takes 2 milliseconds. T2, authentication, follows and takes 4 milliseconds. After T2, T3 fetches data from node A in 6 milliseconds, and T4 fetches data from node B in 3 milliseconds. Both run in parallel, but T5, result aggregation, starts only after T3 and T4 finish and takes 2 milliseconds. Finally, T6 sends the response to the client in 1 millisecond. Considering execution paths, path 1 is T1, T2, T3, T5, T6 totaling 15 milliseconds, and path 2 is T1, T2, T4, T5, T6 totaling 12 milliseconds. Path 1 is the critical path, so any delay in T1, T2, T3, T5, or T6 delays the whole system. Optimizing tasks improves performance in distributed systems. The critical path in this distributed system is T1 followed by T2, then T3, next T5, and finally T6, because this sequence has the longest execution time of 15 milliseconds. This path becomes critical because task T3 is slower than task T4. Even though T4 finishes earlier, the system cannot proceed to result aggregation in T5 until T3 is completed. As a result, T5 is forced to wait for T3. Any delay in T3 directly increases the total response time of the system. Therefore, delays in T1, T2, T3, T5, or T6 will delay the entire distributed application response, making this sequence the critical path. The critical path determines the minimum execution time of a program and limits the maximum possible speedup. Any communication or synchronization delay on the critical path directly affects overall performance. It helps identify the main performance bottleneck in parallel and distributed systems. Optimizing tasks outside the critical path does not reduce total execution time. Schedulers often prioritize critical path tasks to improve efficiency. Program scalability is constrained by the critical path, and runtime variations can change it dynamically. This diagram illustrates the difference between the critical path and the non-critical path in a task graph. Execution starts from the start node, where multiple tasks branch out, showing parallel execution. Each numbered circle represents a task, and the number inside indicates its execution time. The left and middle part of the diagram forms the critical path, which must be completed in a fixed sequence. These tasks depend on one another, so each task can start only after the previous one finishes. The path flows from start through the connected tasks and finally reaches the end node. Any delay in any task on this path delays the entire system completion. On the right side is the non-critical path. These tasks can execute in parallel and do not affect the final completion time as long as the critical path finishes. Therefore, the critical path determines the total execution time, while non-critical tasks have flexibility. This diagram represents a directed acyclic graph, or DAG, of program execution. Each node represents a task, and the arrows show dependencies between tasks. Execution begins at start and proceeds only after all dependent tasks are completed. The sequence 4, 5, 7, E and D forms the critical path. Tasks on this path must execute sequentially and have zero slack. This critical path determines the minimum total execution time of the program. Any delay in these tasks directly delays program completion. All other tasks can execute in parallel and do not affect the total execution time unless they delay the critical path. In a parallel system, the critical path is the longest sequence of dependent tasks within a single system. Tasks execute on multiple processors or cores at the same time to improve performance. Most dependencies occur through shared memory or local task synchronization rather than network communication. Even though many tasks run in parallel, the total execution time is determined by the slowest sequence of dependent tasks. This sequence forms the critical path and controls when the entire computation finishes. Optimizing tasks outside the critical path does not reduce overall execution time. Therefore, performance improvement in parallel systems focuses on speeding up computations on the critical path. For example, in matrix multiplication using 4 cores, the dependent steps T1, T2, and T3 form the critical path and determine the total execution time. In a distributed system, the critical path is the longest sequence of dependent tasks that span across multiple machines or nodes. Tasks execute on different interconnected systems rather than on a single processor. Dependencies include both computation time and communication delays caused by data transfer over the network. Even if some nodes finish early, the total execution time is determined by the slowest task or the slowest network link on the critical path. Optimizing tasks that are not on the critical path does not improve overall performance. Therefore, performance optimization in distributed systems focuses on speeding up slow tasks and reducing communication delays. For example, in a client request workflow, the sequence from request reception, authentication, database access, result aggregation, and response transmission forms the critical path and determines the total response time. Critical path optimization focuses on reducing total execution time. This is done by shortening critical tasks and reducing communication delays. Computation and communication can be overlapped to avoid idle time. Unnecessary dependencies are removed to improve parallelism. Schedulers use dynamic critical path scheduling to prioritize important tasks. Profiling and load balancing help identify bottlenecks and prevent critical path extension. The critical path concept is widely used across different computing and engineering domains. In parallel systems, it helps identify the longest dependent sequence of tasks that limits overall performance and achievable speedup. In distributed systems, it is used to detect bottlenecks caused by slow nodes or delays in network communication. In project management, critical path analysis helps estimate the minimum project completion time and supports efficient scheduling of activities. In cloud computing, it assists in optimizing resource allocation and reducing application response time. In real-time systems, critical path analysis ensures that time-critical tasks meet strict deadlines. In operating systems, it is applied to improve task scheduling, synchronization, and efficient CPU utilization.